Hello guys, welcome back again. Today we are going to discuss singly reinforced beams as per the Indian Standard Code. So before we start, we will quickly discuss the stress strain diagram for singly reinforced beam. So this is the cross section of the beam, this is the tension steel provided at the bottom, this is the strain diagram, and this is the stress diagram. So we will see the basic assumptions that have been considered before designing. It is assumed that the maximum compressive strain in the concrete is 0.0035, while the tensile strain in the steel is 0.002 plus 0.87 Fy by ES, where ES is the modulus of elasticity of steel. This is the stress diagram. Up to 3/7 XU it is rectangular, and for the rest of the depth up to the neutral axis it is parabolic. So we will see what are the values of Cu, whether it is a compressive force and the tensile force. Cu is given as 0.36 FCK XUB, while Tu is given as 0.87 Fy AST. To know where I got these values, you have to see the basic fundamentals, which I'll make a video about this later on. So let's get started with the design of singly reinforced beam. So one thing we have to keep in mind that when we are designing a beam as per the limit state design, the beam cannot be designed as an over reinforced beam. So your depth of neutral axis should always be less than the limiting neutral axis depth, or it should be the limiting neutral axis depth. That is, I want to say that the XU should be less than XU max, or XU should be equal to XU max. So a beam is designed for the maximum moment which it can sustain, that is the moment of resistance for the beam, that is given by the compressive force multiplied by the lever arm. So if we take the compressive force Cu, the moment of resistance for the beam will be given as M ultimate, which will be equal to 0.36 FCK XUB multiplied by the lever arm, that is D minus 0.42 XU. So if you see the stress diagram, this part is the lever arm, that is D minus 0.42 XU. This portion is 0.42 XU. So this is the total effective depth of the beam. If we deduct this part, you get lever arm as D minus 0.42 XU. So your ultimate moment of resistance for the beam will be given as 0.36 FCK XUB D minus 0.42 XU. This will be important for the designing purposes. And another equation you have to use will be, you have to equate the compressive force in concrete to the tension force in steel. That is Cu equals Tu, 0.36 FCK XUB equals 0.87 Fy AST, where the AST is area of tension steel. I hope you got that. So now we'll quickly jump into the problems. So let me tell you one thing, there will be two types of problems. The one would be the analysis type problem, the other one would be the design type problems. In the analysis type problem, you have to find out the ultimate moment of resistance for the beam, while in the design problem you have to find out the area of steel. So basically you have to play with these two equations in order to get the moment or the steel. So let's see the problem now. It's given to us that a RCC section 250 by 600 mm overall depth is reinforced with 425 mm bars, and it is simply supported on an effective span of 6 meters. Determine the maximum yield the beam can carry, and they have given us the grade of concrete as M30 and the grade of steel as 500 Fe500. So first of all we will find out the area of steel. That was 4 bars of 25 mm, so that will be 1963.49 mm square. We need the effective depth of the beam. The effective cover is given as 40 mm, so the effective depth would be 600 minus 40, that would be 560 mm. So the next step, always while designing or while analyzing a singly reinforced beam, first you have to find out the ultimate or the limiting depth of neutral axis, that is XU max. So the first step would be XU max. XU max is given as 700 by 1100 plus 0.87 Fy multiplied by d. This here is the neutral axis depth factor, that is K or KD, whatever you want to call it. So if you put all the values here, the grade of steel is 500 Fe 500 and the depth is 560 mm. So that is 255.37 mm. If you don't want to do this calculations, you can remember some quick values, that is 0.46 D for Fe 500, 0.48 D for Fe 415 and 0.53 D for Fe 250. Okay, so that's what that's XU max. Next step would be to find out the actual depth of neutral axis for the given area of steel. So the next step we have to do is equate the compressive force and the tensile force. The compressive force is given as 0.36 FCK XUB equals 0.87 FYAST. So I'll plug in all the values. FCK is 30, XU you have to find, B is 250, that is the width of the beam, it is given in the problem, equals 0.87 multiplied by Fe 500 steel, that is Fy, multiplied by AST is 1963.49. so your XU would be 316.34 mm. So as you can see in this case, the actual depth of neutral axis is greater than the limiting depth of neutral axis. So it is clear that the beam is over reinforced, and our limit state design doesn't allow you to design a beam as an over reinforced beam. So what we'll do is we will reduce the maximum moment it can sustain by providing XU as XU max. If you reduce the value of XU, automatically the moment carrying capacity of the beam will be reduced. So actually we are designing it as a assuming as a safety factor here. So the third step finally would be, so we can write it here as XU is greater than XU max using XU max. So finally the third step would be to find out the ultimate moment of resistance of the beam, that is mu. Mu equals 0.36 FCK XU max value, because we are taking the XU max value, B D minus 0.42 XU max. So that will be 0.36 multiplied by 30 into XU max value was 255.37 multiplied by 250 multiplied by the effective depth is 560 mm minus 0.42 into 255.37. So if you calculate, you will get 339.74 kilonewton meter. But that's not what is asked in the problem. We have to find out the maximum UDL the beam can carry. So this is the moment, and it is given to us that this is a simply supported beam. So for a simply supported beam, the maximum UDL is at the center, and it is given as M equals WL square by 8, actually MU. So if I plug in all the values here, 339.74 equals W is unknown, we have to find out W. Multiplied by 6 meter is the span which is given to us by 8. So we get W as 75.49 kilonewton. So this value of W is the factored load, because the value of moment we used was the factored moment value. So this will be the factored load. If we divide it by 1.5, we'll get the working load, which will be 50.32 kilonewton. So that's with the analysis type of problem. We'll see the design problem after this. So now let us see a design problem. The problem given to us is calculate the area of steel required for a beam 230 by 390 mm overall depth. It is required to carry a moment of 50 kilonewton meter, and the effective cover is 40 mm. Grade of concrete is M20 and grade of steel is Fe500. So first I calculated the effective depth, that is 390 minus 40, that is 350 mm. So let's start off with the problem. The first step always would be to calculate the value of limiting depth of neutral axis, which is XU max. XU max equals 0.46D for Fe500 steel, which is 0.46 multiplied by 350, which will give me 161 mm. Next step would be calculation of the actual depth of neutral axis. Now you cannot equate Cu and Tu here, because you don't have the area of steel which is in the equation of Tu. So we will go the other way around. As I said earlier, you have to play with these values, these equations. We will use the equation of moment of resistance. M equals 0.36 FCK XUB D minus 0.42 XU. The value of M given to us is 50 kilonewton meter, equals 0.36 multiplied by 20 multiplied by XU multiplied by 230 multiplied by D is 350 minus 0.42 XU. So everything is in place. We don't have the value of XU in this equation, so if we solve for XU, the XU value would be 97.72 mm. So we can clearly see the value of XU is less than XU max, so this beam is an under reinforced beam. So we will not use the value of XU max, but we will use the value of actual depth of neutral axis. As XU is less than XU max, the beam is under reinforced. Okay, so the next step again would be to calculate the value of area of steel. There are two ways to calculate it. The first method is to equate Cu and Tu. Again, you have everything. You have value of XU, AST would be unknown there, or if we can do it quickly, we can use the AST formula directly, which is given as AST equals 0.5 FCK upon Fy 1 minus 0.46 m upon FCK BD square into B into D. So again, this is not a empirical formula. This formula has also been derived from the basic fundamentals. So if I plug in all the values from the previous equations, FCK is 2415, sorry, it's 500, 1 minus under root of 1 minus 4.6, the value of M given to us is 50 to 10 raised to 6 over 20 multiplied by 230 multiplied by 350 square multiplied by 230 into 350. So if we put all of this on the calculator, you'll get the value as 371.41 mm square. So this is the design problem. You got the value of area of steel. You can provide any number of bars as required by you. So that's all with the design and analysis of a singly reinforced beam. I hope you like this video. Please share this video, please give thumbs up, and subscribe to my channel. Thank you so much.